All right, everyone. I am on the line with Gary Ren. Gary is a machine learning engineer at Doordash. Gary, welcome to the TWiML AI podcast.
Hey Sam, thanks for having me.
I am glad to get a chance to speak with you. Yeah, I imagine Doordash is having a bit of a moment nowadays. Things been pretty crazy there.
Yeah, there's definitely been an unprecedented need for our services lately, and yeah, definitely doing our best to make sure that we're available for our consumers, for our merchants, and our dashers.
Awesome, awesome. Well, why don't we start by, as we typically do here on the show, having you share a little bit about your background and how you came to work in machine learning.
Cool. Yeah, so I don't have any kind of super inspirational story about how I got into machine learning, but I will say that I first found out about machine learning when I was in college.
Okay.
I was immediately super interested because it seemed to combine computer science, which is what I was studying at the time,
Hmm.
with math, which is a subject that I've always enjoyed. So after college, I joined the Microsoft Bing Search Relevance team. And while I was there, I got some really good hands-on experience applying machine learning and especially deep learning to search ranking and different natural language processing type of problems.
Okay.
And then I joined DoorDash about 2 years ago. And since then, I've worked on a completely different set of problems, focusing on problems within logistics. And yeah, even though from my work experience, I haven't really used that much math for machine learning like I had initially expected.
Yeah.
All these different ML packages kind of take care of the math for you.
Hmm.
But it's still been super cool to see how, with some lines of code and some math in the background,
Hmm.
you can create these models that can do everything from predict what users are searching for to predict how long it'll take for your food to be delivered.
Yeah.
So yeah, I've been fortunate enough to work on a range of machine learning problems, and yeah, I've really enjoyed it.
Cool. Cool. How long were you at Microsoft before DoorDash?
Yeah, for about 2.5 years.
It's interesting. I talked to a lot of folks at Microsoft and beyond, but Microsoft in particular. There's a ton of talented people that kind of got their start working on Bing, and I think we like to beat up on Bing as a search engine, but the folks that were working on that team are doing pretty incredible things all over the place.
Yeah, I definitely learned a lot from my time there at Bing. And there were tons of smart people working there as well. So it was a great experience for me.
Awesome, awesome. And so I think we'll be following along a general, um, kind of the general discussion that you led at the recent NVIDIA GTC conference, talking about how machine learning powers on-demand logistics at DoorDash. But
Mhm.
before we dig into the specifics of the logistics applications there, maybe tell us a little bit about the kind of the general landscape for ML at the company.
Yeah. So I think to better understand how we're using machine learning at DoorDash, it's best to start by first understanding our business, which consists of a three-sided marketplace. So this includes consumers, merchants, and dashers. And each of these sites, they use DoorDash for a different reason. For example, consumers want the convenience of being able to stay at home while still having access to all their favorite merchants. Dashers want flexible work opportunities, and merchants want to increase the reach and revenue of their business.
Hmm. And dashers are the folks that are delivering the food.
Yep, sorry to clarify. So dashers are the
Yep.
drivers who deliver the food, correct?
Got it. Got it. Okay.
And so yeah, so this three-sided marketplace leads to many interesting problems that machine learning is applied to. So for example, between consumers and merchants, there's a lot of your traditional e-commerce type of problems. For example, recommendations, search ranking. Those are some things that are pretty standard in e-commerce, and those are problems that we have as well. And then between consumers and dashers, there's a lot of problems around balancing supply and demand. How do we make sure that we have enough dasher supply to meet the consumer demand? And some of the ways that we do that is by forecasting demand, forecasting supply, and various levers such as dynamic pricing to try and balance the two.
Hmm.
And then between dashers and merchants, there's a lot of your traditional kind of dispatch type of problems, such as the core assignment algorithm, which is how we find the optimal matching between dashes and deliveries. And so each of these three sides as well, they also individually have their own interesting problems that we can apply machine learning to. For example, for merchants, one challenging problem is how do we predict how long it will take merchants to prepare the food? If it's a pad thai, if it's a pizza, if it's just ice cream that's ready to go, how do we
You
accurately
can't just
predict?
ask the merchant.
Yeah, so we do ask them, but merchants a lot of times, it's very hectic, very busy in the kitchen, and they're not able to provide an accurate estimate either.
Yeah,
And so it's
tell me
super
about
important.
it. I'm
Yeah,
thinking
so
about one of my favorite restaurants here in town. It's a Jamaican restaurant, and they are particularly notorious for, oh, it'll take an hour. You get there, and you're waiting, another hour, for the food. So I need to apply machine learning to that, is what I'm hearing.
yeah, and that's exactly what we do. We definitely take in input from the merchants, and we also use our own historical data to try and augment that and come up with the most accurate predictions possible.
Hmm. Hmm.
Cool.
So the particular application that you presented on was on-demand logistics. Is this one that you personally work on, or is this just one of the many applications at Doordash?
Yeah, so this is one that I personally work on. So I work on the logistics team.
Okay.
And so logistics, yeah, the way I'll explain it is it's kind of the core engine that powers the fulfillment of deliveries on DoorDash.
Mm-hmm.
And so logistics includes many of the problems I mentioned before, such as balancing Dash's supply and consumer demand, as well as the core assignment problem, which again is how we optimally find the matching between Dashers and deliveries.
Mm-hmm. Mm-hmm. And so, kind of walk us through how you approach those kinds of problems.
hmm Yeah, so I would start by saying that the high level goal of the logistics engine is to make sure that we have fast and efficient deliveries. And so what this means is that obviously consumers will hate it if their order takes a long time to be delivered. And so we want our deliveries to be as fast as possible. But at the same time, we want our marketplace to be operating as efficiently as possible as well. And so the way that we do that is in a few different stages. So first is setting up the marketplace by balancing supply and demand. So you can imagine that if we have 100 deliveries, but only 10 dashers, then no matter what else we do in the rest of our logistics system, we're not going to have fast deliveries
Mm-hmm.
because there's 100 deliveries out there and only 10 dashers available to fulfill them. And vice versa, if we have 100 dashers but only 10 deliveries, then a lot of these dashers will be sitting around idle and it won't be a very efficient use of their time. So balancing supply and demand and setting up the marketplace for success is kind of the first step in our logistics system. The second step would be route planning. So once we have these dashers and once we have these deliveries, it's super important for us to plan out the optimal routes for each of these dashers and deliveries. And so you can imagine that there's thousands and thousands of routes that we need to account for in real time. For example, between the dasher and the merchant, and between the merchant and consumer. And so we have to plan for all these routes in real time. And once these are ready, they all get fed into the final stage, which is where the optimal matching happens. So once we have all these deliveries, all these dashers, and all these data about these deliveries and dashers, how do we find the optimal matching between dashers and deliveries in order to have the fastest deliveries possible while having an efficient marketplace?
Mm-hmm.
And so, yeah,
So
sorry, go ahead.
I was just going to say a couple questions jump out at me. One is you've referred a couple times to a logistics engine or logistics system.
Mhm.
Is this a kind of a single piece of technology or literally a single system, or is it a suite of different applications that are used to perform all these different tasks?
Yeah, so it's a suite of different applications. So we have multiple systems that kind of take care of each of these individual components I mentioned. So
Mm-hmm.
we have one system that takes care of balancing supply and demand, another that takes care of route planning, and another that takes care of the actual matching itself.
Mm-hmm. And the way you described it, happening in series, I'm envisioning something that, or well, the question is, are you are you kind of doing the balancing and matching and all this in batches, hourly or something? That doesn't seem like it would work, right? Or is
Mhm.
there a way that you're doing it real time, or what's the granularity that you're making these kinds of decisions?
Yeah, that's a great question. So I'll start by talking about how we do the balancing for supply and demand.
Hmm.
So for this, we actually do it over a pretty wide time range.
Okay.
So several days out, that's when we first start to try and balance supply and demand. So for example, starting today, we'll try to make predictions for what will happen next week. And based on that, we'll already start taking actions to try and balance supply and demand.
Hmm.
For example, if we predict that we're going to get a huge spike in demand next week, then we can take different actions to make sure that we try and get more dashes on the road.
Hmm.
And the reason that we do it so far in advance is because for our dashers, it's useful for them to be able to know when it's going to be busy in the future and better plan out their own schedules that way.
Hmm.
And then once we make this initial prediction, we also continue to update these predictions as we go, and all the way up to real time. And so in real time, we continue to monitor the state of the market. And so we see that we try to check if there's an imbalance between dashers and deliveries. And if so, again, we take different actions to try and balance it. So in real time, if we notice that there's not enough dashers on the road, we'll take different actions to maybe message dashers, telling them that it's very busy right now, or creating more incentives. And vice versa. If there's too many deliveries, then we have levers such as surge pricing, where we'll increase pricing in order to hopefully curb demand. And we can also do messaging to dashers to let them know that, hey, it's not that busy right now, so it might not be the best time to dash.
Yeah. Okay. And so that part of the problem is done kind of over this extended time period. I'm imagining other parts of it, like the kind of core matching has to happen kind of on the fly.
Yep. Yeah. So core matching is definitely more real time. So as deliveries come in, as we predict that they'll be available to pick up. So kind of going back to the food preparation time that we were talking about before,
Mm-hmm.
obviously we don't want to assign delivery right away after the order has been submitted, because a lot of times if the food takes an hour to be prepared, then we will be assigning a dasher way too early. And so once we have these raw inputs from the deliveries, we also make a bunch of different predictions, one of which is the food preparation time. And then again, all these raw data along these predictions get fed into our matching system, which will find the optimal matching. And yeah, this is all done in real time. We get inputs from deliveries and dashes in real time, make the predictions in real time, and then also do the matching real time. One thing we are moving towards, though, and that we are exploring is you can imagine that, for example, as we've grown, we've noticed patterns in where our demand comes in
Mm-hmm.
throughout the day. So, for example, if there's a really popular merchant, then it's not that hard to expect that that merchant will receive some orders during Friday dinner, for example. And so, one of the things that we're exploring is trying to anticipate these orders ahead of time. And then that way we can better position our fleet and better make our assignments to account for these future deliveries.
Okay. Yeah, I was going to ask about that. I noticed for um, scheduled Ubers, for example, the impression that I get is not that it actually schedules the ride, but that it inserts the order for me at the time, before I need the ride, but, kind of real time. There's not really any notion of scheduling. And I don't know if DoorDash has a notion of scheduling. Like, I'd like my dinner at 7 o'clock tonight. And so figure out all the kind of working backwards. And I was curious if that's um, is that based on a lot of experimentation on how to do that, or is it just a simplification that kind of works in the industry for these marketplace types of applications?
hmm Yeah, so we do have scheduled deliveries as well.
Okay.
And I think similar to what you just described, yeah, we kind of just treat them as a regular delivery that happens sometimes in the future.
Okay.
And so for some of the future predicting future deliveries work that I was mentioning, basically you can think of it as scheduled deliveries are kind of future deliveries that we know with pretty much 100% certainty will happen.
Yeah.
Whereas any prediction that we end up making will have some kind of like confidence interval
Okay.
if that delivery will actually occur or not. And so we can treat them in a pretty similar way. But yeah, in the end, they are all accounted for pretty dynamically. Again, we ultimately try to predict when the food will be ready to pick up and assign the dasher based on that time.
Hmm. Hmm. So one of the most interesting aspects of your approach, and you spend quite a bit of time talking about this in your presentation, is that you are pairing machine learning with kind of traditional approaches to logistics optimization. So, maybe
Mhm.
let's dive into that a little bit.
Yeah, awesome. Yeah, so definitely we do make a lot of use of combining machine learning and traditional operations research. And so I'll talk about how we apply this combination to both supply and demand as well as the optimal matching problem. So for supply and demand, like I mentioned, we try and forecast out supply and demand multiple days in advance. And when we determine that we'll have more deliveries than dashers, we'll create these incentives to try and get more dashers on the road. And again, we do that upfront and in advance so that dashers have time to plan out their schedules. And so what this means is that we have to forecast out what demand will be, forecast out what supply will be, and then determine what the right incentive is. And so this gets very challenging. One, because of the complexity. So, for example, if you want to determine the optimal incentive for every single region and every single time of day, that obviously gets very complicated, and there's lots of possible combinations that you can choose.
Hmm.
Another reason it's so challenging is because forecasting itself is always a challenging problem. Forecasting future demand, forecasting future supply, there are a lot of factors that go into it. And especially when you're predicting these things that are so heavily influenced by the real world, it makes it even harder. There's super high variance from things such as weather, traffic, special events, a pandemic. So all these things can have huge impact on our future supply and demand. And so being able to handle all these things is super challenging. And so how we try to solve it is by combining machine learning and operations research. So with machine learning, we try to build out models that accurately forecast out demand and supply. And so once we have these models, what we can do is feed them into operations research system in order to find the optimal incentives. And so the way we do that is by framing it as a traditional operations research problem where we have some objective. And so in this case, our objective would be to maximize our delivery quality. And we also have some constraints. For example, we can't create like $20 incentives. We want to keep costs low as well. And so given this objective of maximizing delivery quality and given this constraint of cost, we can feed our inputs from our machine learning model into the system. And then we can ultimately solve for the optimal incentives by using integer programming. And so this basically treats the problem as a math problem
Hmm.
where, yeah, you have some objective function, you have some constraints, and you solve it through these mathematical methods. And so, yeah, super interesting because otherwise you can imagine that how would you pick like the optimal incentives for every city that Doordash operates in for every single time of day? It gets very challenging. There's so many combinations, and if you have human operators do it, they would have to, manually go through every single region. They will somehow have to try and balance out. Okay, should I add $1 here in San Francisco, or is it better to spend that extra dollar in San Jose? And so by using operations research, we are able to better make these trade-offs and ultimately come up with the optimal set of incentives that again maximize our delivery quality.
Hmm.
And yeah, sorry, go ahead.
Oh no, okay, I was just gonna ask. The You mentioned integer programming. Is it also linear? Like you're using linear programming models, or is it nonlinear OR stuff?
Yeah, so we have a mix.
Okay.
Some's linear, some's nonlinear, and sometimes we also do mixed integer programming as well.
Okay.
Yeah.
And so essentially, you've got kind of these tried and true techniques for, solving these systems of equations, where
Mhm.
you have known quantities, but in your case, some of the quantities you don't know, you don't actually know, and
Mhm.
so you use machine learning to try to predict what those quantities are, and then you kind of pump those into the the traditional OR types of tools.
Yep, exactly. And because of these natural errors in our machine learning models, unfortunately, obviously our predictions are not perfect. So because of that, it's super important for us to have real-time systems in place
Mm-hmm.
to kind of adjust for these errors. And so some examples are what I mentioned earlier, where in real time, we also have monitoring in place to see if there's imbalance in our supply and demand, and it'll take different actions in response to probably essentially try and correct for the mistakes that our more predictive systems have made.
And so when it's in the case of a monitoring system identifying an imbalance, does it is it trying to correct that by, does it just take an action? You've got some kind of program behavior, that is based on what it observes, or does it tweak the inputs and run it through the same system, hoping that you get a better output?
hmm Yeah, so currently the way that we do it is we basically, yeah, once we determine that there's an imbalance, we try to measure how much that imbalance is. And from there, we have a set of actions that we have available to us. And for each of these actions, we try to understand the impact of each of these actions. Again, that becomes like a prediction in some ways,
Mm-hmm.
where we're predicting what the impact will be of different actions. For example, if we message dashers, how many more dashers will we get on the road?
Mm-hmm.
Versus if we add an extra dollar incentive, how many more dashers will we get on the road?
Mm-hmm.
And so we have all these different actions, estimates for the impact of each of these. And based on that, and again, matching that with how much imbalance there is currently, we'll pick the action that tries to fix that imbalance.
Mm-hmm.
And yeah, this is something that we're actively working on and something that we're building out. But that's kind of a general framework where we
Okay.
monitor and we determine how much imbalance there is and choose the action or the set of actions that we think will help us fix the imbalance.
And do you incorporate aspects of control systems, control theory in there? I'm imagining you're monitoring, observing, you take some action based on what you think is going to happen. You kind of overshoot. You might want some dampening in there, or you might need to overcompensate. Do you think of systems in that way, or are you just kind of taking a snapshot in time, and if you're oscillating or not, you're not paying attention to that, you're just making the correction that needs to happen at a given time?
hmm Yeah, so we frequently check the state of our markets in order to try and correct for these actions that maybe we went too far in one direction. And so yeah, we very frequently check the state of a market, and if we notice that, say, we message dashers, but that resulted in us having too many dashers on the road actually. At that point, yeah, we can take additional actions to try and either reduce the number of dashers on the road or maybe curb demand at that point.
Mm-hmm.
Um, and so, yeah, and so another approach that we're exploring as well is framing it as a reinforcement learning problem.
Hmm.
So you can imagine this problem fits pretty well into the reinforcement learning framework, where you have some state, which is essentially the state of our marketplace,
Mm-hmm.
how many dashes there are, how many deliveries there are. You have a set of actions, which are these different levers that we have to try and correct for supply and demand.
Mm-hmm.
And then you have your reward. In our case, it will be metrics about delivery quality and efficiency of the marketplace.
Mm-hmm.
And so, given these settings, it fits pretty nicely into the reinforcement learning framework, where we can explore and exploit, try out different actions, see what the reward is, what the impact is of those actions, and based on that, we can update our models to one, have better estimates of what the impact of different actions are, and two, also allow models to intelligently pick what the best action is at any given state. And so yeah, this is something we're exploring. There's other problems within logistics as well that fits pretty nicely into the reinforcement learning framework. So we think that will be a pretty powerful tool for us moving forward.
Hmm. You mentioned that it sounds like you have kind of boiled all of your customer sat metrics into a delivery quality metric. Is that a metric that you use across the board in assessing the performance of these kind of systems, or is it specific to the reinforcement learning implementation that you're looking at?
Yeah, so it's not specific to the reinforcement learning implementation. We do have these shared metrics that we commonly look at. For example, how fast does it take for a delivery to be delivered? From the time when you place an order to when it arrives at your doorstep, we want to minimize that time as much as possible. And there's other consumer-facing metrics as well that we care about. For example, cancellations. We want to reduce cancellations as much as possible, whether it's because the merchant was actually closed, or maybe the consumer got sick of waiting for so long.
Mm-hmm.
And so a lot of these metrics are pretty common and they're shared across the board by different teams whenever they work on something that could impact these metrics. But again, depending on the project, there could also be more specific metrics that you look at. You can think of these delivery times, cancellations, metrics like that as more of output metrics. But a lot of times we might want a more granular look at what the input metrics look like. And so some examples would be maybe instead of looking at the delivery times directly, maybe we want to focus on looking at how long it took the drop-off to happen. So say we're working on a product that tries to speed up the drop-off process, how long it takes the dasher to drop off the delivery to consumer. And so in that case, it will be useful to look at this more specific metric.
Mm-hmm. And so tell me a little bit about your experiences with the reinforcement learning approach. What have you found there?
Yeah, so it's been still in a more exploratory phase at this point. And I can maybe talk a bit more about some of the results that we got when we tried to apply reinforcement learning to the assignment problem.
Okay.
So again, here, it was a pretty natural fit because we have these states, which again is all the existing deliveries and dashers at any given time.
Mm-hmm.
We have these different actions, which would be all the different possible matching between dashers and deliveries. And so what we've actually tried is, because as you can imagine, if you treat every single combination of dasher delivery pair as the different actions, that action space becomes very huge. So even with 15 deliveries and 15 dashers, there's actually over 1 trillion possible combinations. And so obviously working with that large of an action space is very challenging.
Yeah.
And so what we did was actually we try to simplify and reduce the action space by, instead of using the different combinations of matching as the actions, we just use different variants of the assignment system, of the assignment algorithm as the different actions. And so those were actions. And again, our reward in this case was delivery speeds and marketplace efficiency. And so once we solved the problem this way, we tried using pretty standard reinforcement learning methods. Specifically, we tried using deep reinforcement learning, where our agent was a deep neural network that took in a bunch of features and tried to learn for any given state what was the optimal action to take. And again, in this case, the optimal action is the optimal variant of the assignment algorithm. So yeah, we've done some exploratory work with this. We have a blog post about this on our website actually as well with more details. But we did see pretty promising results where we saw some few seconds improvements in delivery speeds as well as efficiency. And so a few seconds doesn't sound like much, but when you scale it up to millions of deliveries,
for my pizza.
yeah, definitely. But yeah, when you scale it up to millions of deliveries, it definitely adds up.
Interesting. And so what are the challenges? What's keeping you from putting that into production?
Yeah, so I think one is that we definitely just need to keep doing more work to improve each of the components within that reinforcement learning system, improving the deep neural network agent, improving the different features that we have. And of course, our system right now, we don't have a lot of these infrastructure pieces set up. So it would have to require some restructuring and reworking of our system, which again, right now is very much based on using machine learning plus operations research. And so, yeah, there's definitely a lot of investment that needs to be made to move away from the current framework that we have. But again, yeah, we're always exploring, trying new techniques to do things, including reinforcement learning. And as we do more of these explorations, at some point, if we feel that the improvements that we'll get is worth this long-term investment, we'll definitely make the switch then.
Mm-hmm. Is is it possible to um, in thinking about kind of the way you've paired this machine learning system and the operations research system, is it a future direction or of interest to try to kind of collapse this down to a single machine learning system? Is that something that is worth exploration, or if not, why not?
Yeah, I think it is something worth exploring. I do feel that the challenging part of doing that would be that there's certain aspects of the problem that is just very naturally suited for operations research.
Mm-hmm.
And what I mean by that is whenever you have a problem where you have a very clear objective function that you're either trying to maximize or minimize, and you also have very clear constraints, um, it, it's much easier to frame as operations research problem because that's exactly the kind of problems that they're meant to solve.
Yeah.
Where you have some objective, you have some constraints, and you basically frame as a math problem
Mm-hmm.
that's much easier to solve. And so I do think there could be potential for maybe having some kind of like one-shot ML model that can kind of do everything end to end. But right now, I haven't found any great ways of using ML to completely solve these type of problems where you have objective, but then you also have these set of constraints that you must abide by.
Mm-hmm.
And so for us, we found that, yeah, combining machine learning to try and make these predictions, augment the raw data that we have, and feeding it into an optimization system that can take care of handling these constraints for us, take care of maximizing and minimizing the objective function. We found that this approach has worked really well for us.
Mm-hmm. And the operations research elements of this, do they, I'm imagining with the, the kind of the machine learning world where, this is all very new. We're kind of constantly iterating our systems and models and things like that. Is your OR system kind of equal in that way? Are you kind of constantly, tweaking and iterating, or is it, because it's a kind of more mature approach, is it something that once you've identified your constraints and build this pipeline for your inputs, it kind of just does its thing and you don't have to worry about it as much?
hmm Yeah, that's a good question. So it is definitely a more mature field, like you said. But our team is definitely always trying new improvements to it. Some of it could be very small tweaks to the system. For example, tweaking different settings, tweaking different parameters, tweaking different ways of calculating the objective function. And so we're always trying these things. And yeah, you'll be surprised. Sometimes even the smallest changes can lead to some of the biggest gains.
Mm-hmm.
Some of the most improvements that we've gotten over the past year or so have been from very simple changes
What's an
to our
example?
systems. So I can't go into the details, unfortunately, but some examples are basically just tweaking a single parameter,
Okay.
say going from like 4 to 5. And that ends up leading to a pretty big result.
Mm-hmm.
Um, and so yeah, so we always do tweaks like that, and we're always exploring brand new ways of doing the operations research piece as well.
Mm-hmm.
So actually, the switch to using mixed integer programming for our dispatch system, that switch was actually made not too long ago.
Okay.
So we used to use a simpler algorithm that wasn't as efficient because it could only do a single matching at a time.
Mm-hmm.
And kind of recently, we transitioned to this mixed integer programming approach where we can handle multiple deliveries, multiple dashers, and create multiple matchings at a time.
Mm-hmm.
And so, so we're always exploring new options, and yeah, I wouldn't be surprised if sometime down the line we find some new way of doing this optimization that nets us some really big gains.
Mm-hmm. And the mixed and mixed integer programming, does that relate to this idea of multiple inputs and multiple outputs? Or I forget what that specific is. That partial, some floating point, some integer, or is it related to the inputs outputs?
Yeah, exactly. So it's related to the variables in the
Yeah.
optimization problem. So some of them are integers and some of them are floats.
Okay. Okay. And so the how does incorporating floats into your problem allow you to kind of, what I heard was like optimize multiple variables in parallel?
hmm Yeah, so that component isn't what ultimately allows us to make multiple matching in
Okay.
parallel. So the main change is moving towards this just general mixed integer slash integer programming approach.
Uh-huh.
And so before, um, where again our system could only make one pair of matching at a time, and the reason that this was the case was because we were using this algorithm called the Hungarian algorithm,
Okay.
where one it kind of runs pretty slow, especially when you're running it at scale. And then yeah, again, it only does one matching at a time. And so instead, by formulating a problem as a mixed integer programming problem, we're able to not just speed up how fast we're able to solve these problems, but again, also have multiple matching.
Got it.
And once we frame it at this problem, we can continue to have machine learning generate predictions to use as different inputs in the system. For example, we can predict food preparation times. We can predict how long it will take the delivery to be delivered. And based on that, we can create our cost functions, our objective functions, and optimize that way.
Okay. Very cool. Very cool. Uh, were there other points that you covered in your presentation that we should make sure to touch on?
Yeah, so I would say one thing that I wanted to stress as well is kind of just how challenging a lot of these problems are. So I think one thing that I'll touch on is the high variance of our systems.
Mm.
So because we operate in the real world, lots of factors such as weather, such as traffic, special events. Yeah, one funny example is when Game of Thrones used to be on every Sunday evening, we'll see a huge spike in demand. And so even though the last couple of seasons maybe weren't that great, we still had a huge surge in demand, and people were
People were
definitely
still
tuning in.
hungry.
Yeah, people are still hungry. People are still tuning in. And yeah, likewise, whenever we have like the Super Bowl, people definitely tend to order delivery. And so accounting for all these different factors has been super challenging for us.
That's
Um,
kind of interesting from the perspective of tend to think about you kind of build this model and then you put it into production and you want to keep an eye on it and make sure that the data that it sees, looks like the data that you trained it on. But it sounds like you've got all these real world factors that are making the data that the models are seeing in production, look very different. Like, how do you approach? Is there a different way you need to think about model monitoring in a high variance environment?
yeah, I would say you just need to be very careful and very thorough with how you monitor your models.
Can you give
So
us
I
more
think,
detail?
yeah, definitely. Yeah, so I think one general point that I want to bring up too
Uh-huh.
is one challenge that I found with machine learning in the industry is it's not just about finding the right hyperparameters or
Okay.
finding the right model algorithm to use.
Mm-hmm.
It's also involves a lot of general engineering principles as well.
Mm-hmm.
To deploy machine learning to solve your problems in a reliable and scalable way, there's a lot of systems that you have to set up in place. Yeah, one example would be how do you make sure that you monitor any degradation in your models?
Yeah.
How do you make sure that there's consistency between the data that you saw during training and the data that you see during prediction?
Mm-hmm.
How do we manage and run experiments with different versions of many different models? How do we periodically retrain these models? As they degrade, how do we make sure that they get retrained and updated with the latest data? And of course, yeah, like how do we protect against incorrect predictions? In cases such as, yeah, when a pandemic hits,
Mm-hmm.
our models are always going to struggle at predicting that. So how do we make sure that we account for these incorrect predictions and adjust accordingly? And so we've invested a lot of time and effort into building out engineering systems that can take care of these things for us. So setting up monitoring of our model predictions, monitoring of our model inputs, making sure that the data that the model sees is always what it expects. And if we notice anything wrong, anything that deviates from what's expected, whether it's the model output or the input data into the models, we can take different actions to try and fix that. So one example is if we see that the model accuracy is slowly degrading over time, then we can retrain the model. And we have systems set in place as well so that these models are automatically retrained. And so when it's time to replace it, it's a pretty simple switch where we just plug and play in the new model. Other cases, it might be more complicated. So for example, when there's a pandemic again, our model obviously didn't generate very accurate predictions in those cases. And so that might prompt us to look into, maybe there's some features that we want to add that will help us better correct for any errors we have. And maybe aside from just improving the model itself, maybe that tells us that we need to build more real-time systems in place. And these can be augmented with machine learning, or they could just be simple, using simple heuristics that try and detect model errors and then take different actions to account for them. And so this kind of goes back as well to how we balance supply and demand, where again, we have all these predictions, we do all these things ahead of time, but ultimately in real time, we know that we're not going to have a perfect system and there's still going to be imbalance in real time. And so we spend a lot of time in building out this real-time monitoring, this real-time system that can take actions to correct for any issues that we see.
Okay. In the case of the onset of coronavirus, I'm imagining you saw your models, not working the way that they otherwise would have. Were your existing model monitoring and retraining, tech and procedures kind of enough, or did you find you had to do like a lot of manual overrides to kind of make it through because it was unprecedented times and all that?
Mm-hmm. Yeah, so we definitely use a mix of relying on our existing systems that automates a lot of this monitoring, retraining, plus some manual actions on top of it as well. So a lot of times, like the day of, for example, when shelter in place first started, or when the stimulus checks first went out, those are things that we're not able to, our systems are not always able to react as quickly as we would like.
Right.
For example, if we were to retrain a model, we would need new data to come in first before we can retrain it. And so in those cases, we definitely have operators who will, again, help with monitoring our systems. And if they notice any drastic changes that our automated systems are not accounting for and are not adjusting well enough for, they will take additional actions on top of that.
Okay.
And so this is something that we always have in place. It's not something that we just do because of COVID. There's always like interesting cases here and there where we have these like super drastic events that requires additional manual intervention. And so, so we do still rely on a mix of automated systems as well as human intervention.
Got it. Cool. Well, Gary, thanks so much for taking the time to share some of that with us.
Yeah, thanks, Sam. Thanks for having me.
Awesome. Thank you.